extreme, yeah, followed by the thunder, the huge thunder.
Yes, yesterday was really horrible, Fitri.
Yeah, very
right.
horrible.
So it's a
Hopefully
bit. So in Australia, the Christmas is not white Christmas, yeah, because it's
No.
happen in summer.
Yeah, that's right.
Okay.
So we have like a barbecue Christmas.
Okay. Yeah. Okay, Bu Vidya, shall we start?
Yeah,
Okay.
it's 4:22.
Ya, oke.
Yeah, please guys.
Ya, baiklah Ibu dan Bapak serta adik-adik mahasiswa, kita akan memulai kuliah umum dari Prof. Naresh Kumar dengan topik yang masih sama sebetulnya dengan yang kemarin, yaitu tentang structure and reactivity of polyfunctional compound reaction of dicarbonyl compounds. So, welcome for all of you to the program of Visiting Professor Lecture Series from Chemistry Department of Universitas Pendidikan Indonesia on Organic Chemistry with Prof. Naresh Kumar from UNCW, Sydney, Australia. So I'm Siti Aisyah, and it's my pleasure again to be the moderator for this session on the title of Structure and Reactivity of Polyfunctional Compound Reaction of Dicarbonyl Compounds. Prof. Naresh, without further ado, I would like to welcome you to deliver the topic. The time is yours, Prof.
Yeah, thank you very much. I will start sharing my screen so that you can see my slides. That's my screen here, and
Yes.
I'll just go to full screen and find a pen so I can write on the screen. I just double check that I can do it. Just give me 1 second. Just pen color. Yeah, red is fine. Yeah, I got the pen. Okay, what we're gonna do today is continue on the theme of the dicarbonyl compounds we started in the last lecture. And hopefully we'll finish the remaining slides related to the reactivity of the dicarbonyl compounds. You may recall that we left last week on this particular slide here, where we talked about thermodynamic versus kinetic enolates, thermodynamic versus kinetic. And thermodynamics and kinetic enolates became relevant because when we looked at the carbonyl compounds which were unsymmetrical, that means the alpha carbon here is different from the carbon over there, then there are two possibilities to form enolates. One enolate is on the left-hand side to give you this particular enolate here. You remove this particular proton because this is a CH2. It has two protons present on it. And if you remove one of that protons with a base, you will get the corresponding enolate on the left-hand side. And this is a less hindered site because it's just hydrogen. So that means a big reagent can come on this side quite easily. While on this side, there is also a hydrogen present at this position. And using a base, you can also remove that hydrogen. But the problem here is this side is going to be a little bit blocked because there's a methyl group present at that carbon. So that means if you have a hindered base like LDA, we talked about LDA in the last lecture, that is like a hindered base, and the hindered base can come very easily on the left-hand side to remove this proton. Although this enolate here is more stable because this enolate is highly substituted. So whenever you have a situation where the double bond is highly substituted, that is thermodynamically more stable situation. So this enolate is more stable than this one because this is less substituted. By less substituted, we mean that it has a hydrogen here. And if you compare that double bond with this double bond here, this double bond is more substituted. So this is more stable enolate. So the one which is formed readily and quickly with a strong hindered base is going to be the one on the left-hand side, and we call that a kinetic product. That means it's formed faster. And because the hindered strong base removes the less hindered proton, that's the reason why this side is the kinetic product, even though it is a less stable product. On the other hand, if you look at this enolate here, which is more stable, the double bond is more highly substituted. So if you leave this kinetic product sitting around for a long time, you will find that slowly it will convert back to the thermodynamic product. So that means you have to do this reaction fairly quickly to get the kinetic product. Otherwise, it will go towards the more stable form of the product. And indeed, if you use a weaker base, then the weaker base acts slowly. So that means the thermodynamic product will predominate in that reaction. So theoretically, you can either get this product if you use a hindered base, or you can get the product forming on the right-hand side if there's a weaker base. So if we took this compound here and reacted with the methyl iodide, say for example, CH3I, in the presence of a hindered base, the product, the kinetic product that will form will be the product where you will have the methyl group going towards the kinetic side. So you will have the methyl group going over here, and your starting compound already has a methyl group here. So this will be the product that will predominate in this reaction. CH3, CH3, if you got a hindered base and methyl iodide to do the reaction. Sorry, it's a bit slow. Okay. But if you treat it with a weaker base can be sodium hydroxide, can be sodium ethoxide. And what you will find is that the predominant product that will be formed in that reaction will be where the methyl compound, methyl iodide, will react on the same carbon where you got the methyl group present already. So that means the product will be the thermodynamic product where you will get this particular compound being formed. Okay. So there's a difference between a kinetic product and a thermodynamic product. And that comes about from the unsymmetrical ketone which you had. Okay, so this is the product which is the kinetic product, and this is the product that is thermodynamic product. And if you're using a weaker base, then this will be the predominant product, this will be the major product. And if you use a strong base and strong hindered base like LDA, then you will get this as a product forming in that reaction. So LDA will give you the major product over here. And if you use ethoxide, say sodium, sorry if I can draw sodium ethoxide, which is a normal base used in organic chemistry quite a bit, Na+, and OET minus is sodium ethoxide. Sorry if I can draw it quickly, it's just a bit slow, this pad here. ET minus will be the major product shown over there, which will be your thermodynamic product. So typically, when you react carbonyl compounds like cyclopentanone or cyclohexanone, and you're not careful with the condition and the temperature, you will find that you will get mixtures of products forming in that reaction. So you have to, so you have to be
sorry, Prof. Naresh. Host, Bu Amel, can you? Okay. Yeah, thank you, Bu Amel. Yeah, you can continue.
Sorry, Prof.
No worries at all. So what happens is, if you're not careful in these reactions, so this reaction is typically carried out at quite low temperature. And if you are not careful with the temperature or the conditions in this reaction, you can get a mixtures of products because the reaction can go in any direction and lead to mixtures of products. So there is one way to control this reaction, and that is to use what we call an enamine. I don't know, you might have heard about enamines in your first year carbonyl chemistry when you were looking at the formation of imines and enamines, carbonyl compounds reacting with amines. So for example, this enamine is derived from reacting a cyclohexanone compound, a ketone compound, with a secondary amine, which is your pyrrolidine in this case. If you do the reaction of this amine with the carbonyl compound, you will find that the product you will get in this reaction will be the enamine shown over here. And if you compare an enolate with an enamine, you can see that there are similarities between the enolate and the enamine. So the enolate has an oxygen attached to the carbon with a negative charge. Enamine has a nitrogen attached to the double bond, also having nitrogen pair of electrons. So nitrogen has pair of electrons. So that means in terms of reactivity, the enolate is a very similar in reactivity to an enamine. And also we know that the enamine can be hydrolyzed back to the ketone compound as well after it is formed. So that the question then is, can we, instead of enolate, use an enamine to do the same reaction? So in the alkylation reactions we just learned is that the enolate, this enolate is in resonance structure with the corresponding carbanion compound. So this is resonance structure for this compound here, right? This is what we learned in the last lecture. So these are resonance structures. So what happens is that the attack of that carbon over here onto the alkyl halide gives you the corresponding alkyl product. The same chemistry can also be done with enamine, where the pair of electron comes around and you can alkylate that alpha position in enamines with an electrophile like an alkyl halide. We also know from our first year chemistry that the imines can be hydrolyzed, or enamines can be hydrolyzed to the corresponding carbonyl compounds. So that means you can hydrolyze this compound to a carbonyl compound and you will get the same product. And that is shown in the next slide, the whole reaction sequence. The cyclohexanone reacts with a secondary amine like pyrrolidine in the presence of an acid catalyst to give you an enamine. This is something you should have learned in the chemistry of carbonyl compounds in first year. And then the reaction of this enamine here reacts the same way like an enolate to alkylate this position over here. And then this ammonium salt here can be hydrolyzed in the presence of water to give us the alkyl substituted compound. So it's exactly the same reaction by using a base and reacting it with methyl iodide, but going via the enamine rather than enolate. The advantage of going via enamine is that this reaction doesn't require any hindered base. It doesn't require a very reactive base. And this reaction always gives the mono-substituted compound. You only get mono-alkylation reaction in this sequence. So this is an alternative to using a very expensive, very hindered base, while you can do this reaction by exploiting the chemistry of carbonyl compound with amines and then achieving the same result at the end of the day. So this is using enamine as a surrogate for a carbonyl compound to do the same reaction like we discussed before. Okay, now let's move on to compounds which have two carbonyl groups rather than one carbonyl group. And we're going to be particularly looking at compounds where the carbonyl compounds are present in 1-3 relationship. So if you call that as 1, this has 2, and this has 3. So in all the cases we're going to be looking at the carbonyl compounds where the relationship is 1-3. And if you look at the pKa number underneath these compounds here, that represents the acidity of this CH2 group, which is present. So the first compound is the diketone compound. This one is a keto ester, and this one is a diester compound. And lower this number means more acidic that CH2 is. That means more easy to remove that proton by a base. And these are like doubly activated CH2. Because the earlier example we saw on the last slide, for example, was that there was only one carbonyl present in these compounds, and there was CH2 which was present adjacent to that carbonyl group. So there was a hydrogen here, and there is another hydrogen here because this is a CH2 group next to the carbonyl. But in these 3 compounds you got here, you can see that the CH2 has 2 carbonyls present next to it. While this methyl here is also next to the carbonyl, but it is less reactive compared to the CH2 because the CH2 is surrounded by 2 carbonyl groups. So that means that CH2 is more acidic than this CH3 over here. So that means in the reaction of these compounds, the CH2 will react preferentially over the CH3, which is adjacent to the carbonyl group. So they're like doubly activated, and they're much stronger acids. And simple bases like sodium ethoxide is good enough to remove this proton, which is present in these compounds. By the way, if you don't know how do we get sodium ethoxide, sodium ethoxide is very easy to make in the lab. We take sodium metal and we react the sodium metal with ethanol. And if the ethanol has to be dry and absolute ethanol in this reaction, because you don't want water present in your ethanol if you're adding sodium, because sodium reacts very violently with water. But if you take pure dry ethanol and you add sodium metal into it, you generate this base called sodium ethoxide. And sodium ethoxide is a good enough base to remove that proton in these cases. And this is going to lead to very interesting reactions, and we're going to see that in a minute. We're going to start with malonate. This compound with 2 carboxylic esters is called as a malonate. And this one is a keto ester. And we're going to be looking at the reactions of these 2 tonight. So let's start with the malonic ester or ester compound. We call that a malonate because malonic acid has this structure. If you take CH2 here and put a carboxylic acid on this side and carboxylic acid on the other side, that compound is called as malonic acid. So this compound here, if you have a carboxylic acid on this side and on the other side is called malonic acid. So this is just a malonic ester, and it's a diethyl malonic ester or diethyl malonate. If you take the base, which I just told you we generated in the last slide, you will remove this proton here from the CH2. And if you react it with an alkyl bromide, you will put that R group onto that carbon over here. And if you work up your reaction with aqueous acid and heat the reaction mixture, you will find that one of the carboxylic ester group is lost in this reaction, and the CH2 and the acid component from the malonic acid gets added to the alkyl halide. So we started with RBr, our alkyl halide, and the product we get from that reaction is RCH2COOH. So basically we have removed that bromide from the R and added CH2COOH. And so this reaction is a very, very useful reaction to convert an alkyl halide into a carboxylic acid. And in the process, we add 2 extra carbons to the alkyl halide. We'll see some examples in a minute. If this alkyl halide was 4 carbon, the corresponding acid you will get will be a 6 carbon acid. And you're also wondering what happened to the other carboxylic acid as well, and that becomes clearer when we go to the next slide. So this is the mechanism now shown for this reaction. How does it work? This is our ethoxide base. That's the sodium ethoxide. And it is good enough to remove one of the protons from the CH2. And once the proton is removed, you generate this carbon ion, and this can be stabilized by enolization with that double bond, or resonance structure with that double bond. And then this carbon ion can attack the alkyl halide, kicking out the bromide, and you introduce the R group at that position. Okay. And then when you add aqueous acid and heat up this mixture, you will find that the esters can be hydrolyzed in the presence of acid to the corresponding carboxylic acids. And the carboxylic acid, when you heat it, one of the carboxylic acids is lost as carbon dioxide. So one of the carboxylic acid is lost as CO2, and the product you get is RCH2COOH. So basically, bromide is gone, and you added a CH2COOH to your compound. Another interesting thing about this intermediate here is, if you look at this intermediate here, you also still have a proton which is quite acidic. So this proton in the center is quite acidic. You can actually remove that proton as well and add another alkyl halide over there at that particular carbon. And we'll see that in a minute. But this is the overall mechanism for this reaction. And why is it so easy that this carboxylic acid is removed? Normally, it is not very easy to chop off carboxylic acid groups from the molecules. But this is a special reaction when you have 1,3-dicarbonyl compound, and one of the carbonyl group is carboxylic acid, that can be decarboxylated quite easily. The reason for that is that it has this intermediate structure that is possible. So when you hydrolyze this diester to the dicarboxylic acid, this concerted reaction can take place. This pair of electrons can move here. This bond is broken, and then this moves over here. So what happens is that the left-hand side of the molecule is removed as CO2, and the right-hand side of the molecule is RH, double bond, COH-OH. And this is basically an enol form of carboxylic acid, and this can tautomerize back to the corresponding carboxylic acid. So this decarboxylation reaction only happens when you have a carboxylic acid and a carbonyl compound. And this group here doesn't have to be a OH. This group can be simply an R group here, but one of the side has to be carboxylic acid, and the other one can be any ketone, and you will get that decarboxylation happening. So that's a very common reaction of the 1,3-dicarbonyl or beta keto acid compounds, we call them as well. So this position is called as alpha, and this position is called as beta. So this is an alpha beta carboxylic acid. So that's the reason why it decarboxylates so readily. Okay. Now, I was telling you earlier that once you've done one alkylation, so the first 3 schemes here, part of the scheme is exactly the same as before. You have malonate, we remove the proton, we do alkylation at this position. And I was telling you that this CH is still an acidic CH. That means you can remove that proton also with a base, and you can add another alkyl group at that carbon over there, and that alkyl group R dash can be same as R or it different. So you can have either the same alkyl group or different alkyl group added at that position. You can hydrolyze this ester to the corresponding carboxylic acid, and then you heat it, and one of the carboxylic acid is decarboxylated, and you ended up with two alkyl groups present at that carbon and a carboxylic acid present in the molecule. So it's a really useful reaction in not only making normal carboxylic acid, but also can make substituted carboxylic acids as well using this malonate alkyl halide chemistry. Now let's look at some real example here and see what products you're going to get. And I'm going to ask you a question after a couple of slides and see if you can come up with the answer by yourself. So the question, the example we are looking at here is 1-bromobutane. That means 4-carbon alkyl halide, that's 1-bromobutane, is reacted with malonate in the presence of sodium ethoxide base. And we want to find out what the product of this reaction will be. So basically, ethoxide will remove one of the protons from malonate. So this is a slightly different way of drawing the malonate we've been drawing. So this is exactly the same as CH2 having an ester on this side, CO2 ET, and also the ester on the other side. So it's just a different way of drawing diethyl malonate compound. So if you can draw another ester on this side, sorry, my keypad is playing up a bit, CO2 ET. So it's exactly the same as that compound over here. There's no difference. We just have written it slightly differently. With base, you remove one of the protons. Alkyl halide will then react with your the intermediate anion, and bromide is kicked out, and you get this diester compound. And when you hydrolyze it in the presence of aqueous acid, one of the carboxylic acid will be lost because it'll be hydrolyzing to the carboxylic acid first. And once the carboxylic acid is formed, then one of them decarboxylate and you get this product. So if you compare the starting material with the product, you will find that this compound now has an extra CH2 COH group, and the 4 carbons from the bromobutane are still there. There's 1, 2, 3, 4. And this CH2 COH is coming from your malonate. And the compound, instead of being a 4-carbon compound, now it's a 6-carbon compound called hexanoic acid. So the beauty of this reaction is that you can add a CH2 COH into a molecule and increase the chain length. What about if I use the intermediate which I have already? So I have this intermediate compound in 84% yield, and I want to put another alkyl group at this position. I can do that quite easily, and I can get a substituted acid in that case. And this is shown on this slide here. So we take this intermediate which we had from the last slide, we treat that with a base again, and we remove this proton because this is an acidic proton. And then we reacted with the methyl iodide this time, and we put a methyl group on this particular carbon over here. Instead of CH, it becomes a CCH3. And now if you hydrolyze and decarboxylate, this is the end result where CHCO2H is coming from your malonate, and the 4 carbons are coming from one alkyl halide, that's bromobutane, and the second methyl group is coming from methyl iodide, which is your second alkyl halide. And the end result is that you end up getting a substituted hexanoic acid. So you can manipulate this reaction in any way you like to generate straight chain carboxylic acids or substituted carboxylic acid. You can even take this reaction one step further. You can even make cyclic carboxylic acids. And the way to make cyclic cyclic carboxylic acid, which is shown with an example of cyclopentane carboxylic acid here, is that instead of starting with two different alkyl halides, you can have alkyl halide present in the same molecule. This can be a 4-carbon dialkyl halide, can be 5-carbon dialkyl halide, can be 6-carbon alkyl dihalide. It's really up to you. And the beauty of having the two alkyl halides in the same molecule is that you do the first reaction by forming the anion, treating the malonate with sodium ethoxide, reacted with one alkyl halide, you will get the top part of the molecule. And then you can still remove this proton here because this proton is acidic next to two ester groups. And then you can get the second reaction from that carbon onto the alkyl halide, kicking out the Br out. And then you get the diester here. And if you hydrolyze this diester to the carboxylic acid, you will get the monocarboxylic acid compound. You might wonder how this compound looks like. This compound simply is, sorry, I just trying to draw the 5-member ring. This compound simply is, I'll just try to draw it here so there's a bit more clearer, just like this. So you have 5-member ring and you have an ester attached here. So that ester will get hydrolyzed to the corresponding carboxylic acid and also another carboxylic acid over here. So when we are writing these two esters in the bracket like that, it means that carbon in the center has two carboxylic esters or acids attached to it. So after you treat it with acid, it hydrolyzes to dicarboxylic acid. And one of the carboxylic acid is then lost as CO2, and you get a cyclic carboxylic acid, which is a cyclopentane carboxylic acid in this case. If you start with a 5-carbon CH2 dibromide here, you will get a 6-membered carboxylic acid forming. So you can manipulate this reaction to generate straight chain, branched, cyclic, any type of carboxylic acid you want. So it's a really, really facile reaction and very easy to do. So I got a couple of questions here for you. So the question is, what alkyl halides are needed to prepare each carboxylic acid by malonic ester synthesis? So we are giving you a hint here already that these compounds are going to come from malonic ester synthesis. And the question is, what is the alkyl halide compound that is needed to prepare this compound here and this compound here? And it says halides. So that means either one or two alkyl halides may be needed to prepare this starting compound. So that's question 1. And this one is question 2. So they're two separate questions. So I want you to think about it for a couple of minutes and then see what answer you come up with. I'm going to give you 2 minutes or 1 minute to think about it so that you can think in your own mind what could be the answer. And then I'm going to show you what the answer to this question is. Just give you 1 minute to think about it. Okay, I hope that everybody got the answer already. If you think back, what I've been telling you is that CH2COH portion of the molecule comes from the malonic acid and the rest comes from the alkyl halide. So you can happily say that the starting compound or the alkyl halide you're going to need from this reaction is going to be the CH2 here and then CH here. And then you're going to need 1, 2, 3, 4 CH2. So I'm not going to draw all those 4 CH2. They'll take too long. I'm just going to put CH2 in the bracket 4 times and the bromide next to it. So this is the alkyl halide you will need to prepare this compound by Malonic Ester. What about this one here? This one here has a CH-COOH, and this part of the molecule is coming from the Malonic Ester, and the remaining parts are coming from the alkyl halides. So that means it requires two alkyl halides. One is going to be like this, just the same Br over here. So it's going to be alkyl halide over here like that. And the second one is just 1, 2, 3 carbon long. And that's going to be your corresponding Br over here. So it's going to need two alkyl halides. You do sodium ethoxide, react it with one alkyl halide, then add second ethoxide, and then react it with the second alkyl halide and hydrolyze and decarboxylate. And this is the product you get. It doesn't matter which order you do it in. You can react it with this bromide first and this bromide second, or this one first and the other one second. The product will be the same. I hope you all got that, but if you haven't, that's the answer. Okay, can we extend this reaction a little further? Can we, instead of the diester, start with a compound which is one ketone and one ester? And the most common chemical in this series is what we call ethyl acetoacetate or acetoacetic ester. That's a very cheap, easily available starting material. You can buy that in a bucket quantity, very, very cheap. And if we do the same reaction with the alkyl halide here, what product we will get from that reaction? So what's going to happen is, just like last slide, you're going to be able to remove that proton which is there, and you're going to add your alkyl halide over there. And then you got an ester group present on this side, and that ester can be hydrolyzed and decarboxylated, while the other side is a ketone, so that cannot be decarboxylated because it's not an ester. So that's going to stay in your product. And the end result is going to be that you're going to add a CH2COCH3 to your alkyl halide in this case. In the Malonic Ester, we added a CH2COOH or a CH-COOH. Here, we are adding a CH2COCH3 to your molecule to give you a ketone compound. So the alkyl halide here got converted into a ketone compound with 3 extra carbons attached to it. Again, a very useful reaction in terms of the extending the chain of a given compound. The mechanism here is exactly the same as the Malonic Ester. Only difference is that the starting material is different. Instead of 2 esters, it has a ketone and an ester functionality. The mechanism is exactly the same. You remove this proton, you react it with alkyl halide, you put an R group here, you hydrolyze it with aqueous acid to get the mono acid in this case. And when you heat it up, the relationship between these 2 carbonyls is still 1 to 3, and this carboxylic acid can be removed as CO2 to give you that product, where the black portion of the molecule here comes from the starting acetoester, and the alkyl halide is represented by R. So a very easy way of making extended ketone compounds. Just like before, you can also add another group here because this CH is still acidic, and you can get a more substituted compound from this reaction as well. But let's look at one example. Just like before, we start with a 4-carbon alkyl halide, and we react it with sodium ethoxide and the acetoester. And same way, we get the substitution at this carbon here. You hydrolyze and decarboxylate, and the 4-carbon here becomes 7-carbon long. Heptanone is 7 carbon, and this 3 carbons here in that molecule, CH3, COCH2, comes from acetoester, and the 4-carbon component here comes from your alkyl halide, present in your starting material. So you get from 4 carbon to 7 carbon compound. You converted an alkyl halide into a ketone compound by using this simple carbonyl chemistry. And this acetoester doesn't have to be in an open chain form. So the acetoester we looked at so far has this structure. It was CH3, a CO, and it had, and it has a C double bond O, and it had a CH2, and it had a ClET over here. That was the starting compound we looked at in the last few slides, where we have this as your starting material, right? This is the CH2. So the key was that there is a CO, there is a CH2, and there's an ester. That was in an open chain form. You can have that CO instead of CH2 as CH and an ester in a cyclic form. So this keto and the ester group doesn't have to be in an open chain form. It can be in a cyclic form as well. And it'll do exactly the same chemistry, because we know that this proton sitting here at the junction is an acidic proton. And if you treat that with a base, this proton is removed, just like this proton can be removed. And then you react it with an alkyl halide. So the alkyl halide here is what we call a benzyl bromide, phenyl CH2Br. It doesn't matter what is attached to this CH2 group. The reaction is going to be the same. So this compound, the anion here, is going to attack that CH2 over there, and it's going to kick out that Br to give you a substituted compound over there. And you can see now that this carbonyl here and this ester here, they are still in 1 to 3 relationship. So that means this ester here can be hydrolyzed to the corresponding carboxylic acid, and then it can be decarboxylated quite easily to the corresponding acid compound. This is then decarboxylated to give you that product. So that means you basically introduced a CH2 phenyl group at that position where the ester was, in this case, exploiting this acetoacetic ester chemistry. And similarly, like we saw before, if you have malonate, you could get cyclic carboxylic acids. If you have a dihalide compound and you do the reaction with the acetoester, you can get cyclic ketone compounds as well, doing the same chemistry in this case. The only difference is you got a different starting material in this case, which is an acetoester compared to a malonate ester. The underlying chemistry is exactly the same. You generate the carbon ion, which then attacks your CH2 and then kicks out one of the Br first to form that carbon-carbon bond over here. And this proton is still acidic, and you can remove that proton with a base, sodium ethoxide, and then this carbon here will attack that CH2 and it'll kick that Br minus out, and you will get this compound where you have an acetyl group and a carboxylic acid group present on the same carbon. But the relationship between this carbonyl and the ester is again 1 to 3. So that means this ester here can be hydrolyzed to the corresponding carboxylic acid, and then you can decarboxylate it as CO2 to give you a cyclic compound with a COCH3 group. If you start with a 5-carbon dihalide compound, you will get a 6-membered ring. Exactly the same chemistry as the malonate, but because you're starting with an acetoester, you will get a ketone compound forming in this reaction as shown here. Okay, I have a question for you again. The question is, what alkyl halide or halides are needed to prepare each ketone using acetoacetic ester synthesis? So you're given 2 products and you're asked what starting alkyl halide or halides I will need to prepare these ketone compounds. Again, I'm going to give you 1 minute to think about it, that what alkyl halide you will need. I can give you a hint. Think about what part of the molecule is going to come from the acetoester, and the remaining is going to come from the alkyl halide. So give you 1 minute to think. You got the answer? If you think about it carefully, this CH2, COCH3 comes from the acetoester. And what is remaining is basically a CH2 and a CH3. And all you need to do is to add an alkyl halide. So it's CH3, CH2, iodide or bromide, it doesn't matter. That's the alkyl halide you're going to need to do this reaction or to make this compound. This one here, this part of the molecule is coming from acetoester. And then there are 2 alkyl halides remaining there now. 1, 2, 3, 4. So one of them is going to be a 1, 2, 3, 4 carbon and a bromide or an iodide here. So you go 1, 2, 3, 4, 1, 2, 3, 4. Okay. And the bottom here has got 1, 2. So basically you're going to need some sort of alkyl halide like this, which is 2 carbon long. This is CH3, CH2Br. So it's the same thing. So acetoester, and these are the 2 alkyl halides you're going to need. And again, it doesn't matter whether you start with 4 carbon halide first or 2 carbon halide here, end product is going to be the same. Okay. So if you get a question like that or see a structure like that, don't get alarmed. Just think what part of the molecule can come from the acetoester or malonate ester, and what else I'm going to need to get there. Easy thing to do. Okay, let's change reactions a little bit and talk about a second possible reaction, which is there also in the case of carbonyl compounds involving the carbon that is present adjacent to the carbonyl functionality. So I got 2 simple molecules written here. One is acetaldehyde, that's 2 carbon aldehyde, and acetone, a very common solvent molecule. Now think about it. If we've been saying in the lecture last week and today also that the CH2 or CH3 adjacent to a carbonyl is acidic. So that means in theory, we should be able to generate, or we have shown that we can generate quite easily the corresponding compound, which is the carbon ion compound, which is then stabilized to give us the enolate compound. So we can remove this proton quite easily, right? We've been learning all along in the last week's lecture and today's lecture like that. But we also know from our first year chemistry, which I also covered in the introductory slides last week, that a carbonyl compound by nature has got a slight negative charge on the oxygen and a slight positive charge on carbon, because oxygen is more electronegative. So this pair of electrons is more towards oxygen than carbon. And we know from our first year carbonyl chemistry that if you have a nucleophile either as a minus or nucleophile as a lone pair of electrons, that nucleophile will attack the carbonyl group, carbon, and move this pair of electrons over here like that to give the corresponding alcohol. This is first year chemistry where we know carbonyl compound reacts with nucleophiles to give addition products. Now, if we generate this enolate here by treating the carbonyl compound with a base, you can imagine that this anion here can also react with this carbonyl compound, which is present in the starting material itself, to give you a condensation product. So the acetaldehyde compound, if you take two here means two equivalents. One equivalent, if you form the anion, can attack the carbonyl in the second equivalent to give you this intermediate compound here, which we call beta hydroxyaldehyde. And again, the term beta comes about alpha and beta from Greek alphabets, just like A and B, B is beta. So you will get this compound called hydroxyaldehyde. And this reaction is reversible. You can see that it's not written in a direct arrow. And the same thing applies to acetone as well, that in acetone, you can also remove one of the protons from the CH3 to generate CH2 minus, and you have a C double bond O, a C double bond O here, and a CH3. And this then can react with the carbonyl compound, which is your starting material itself, to attack at this carbon over here. And this pair of electrons can move over here to give you this intermediate or the beta hydroxyketone in this case. So that means the carbonyl compound having a active CH2 or CH3 group adjacent to it can react with themselves to give us this hydroxyaldehyde or hydroxyketone product. What is the mechanism? I've given you some of the mechanism already in the last slide. The base removes this proton adjacent to the carbonyl group to give you this carbanion here, which is then resonance stabilized to form this enolate. And enolate is the reactive species. In this case, the net result is attack of that CH2 onto the carbonyl to give us this intermediate alkoxide, which then gets protonated to give us the corresponding hydroxyaldehyde. So the mechanism is pretty straightforward. You remove the proton from the adjacent carbon, that becomes a nucleophile, attacks your carbonyl, and protonation gives you the corresponding hydroxyaldehyde or hydroxyketone compound. And one thing which can happen with these hydroxy compounds is that this is the hydroxyaldehyde we just got and hydroxyketone we just got in the earlier slides. You can remove a water molecule from these hydroxyaldehydes and hydroxyketones quite readily. The reason is you can imagine that this proton here adjacent to the carbonyl is still an acidic proton. So if you remove that proton, you can then get rid of that as a hydroxide minus, or if you protonate that with an acid, form an OH2 plus, you can then dehydrate to get the corresponding alpha beta unsaturated compound. So by alpha beta unsaturated compound, we mean this is the alpha position and this is the beta position. Unsaturated means that it's not saturated, there's a double bond present, and it's highlighting that there's a double bond present at that position to form that alpha beta unsaturated carbonyl compound. So one thing which can happen with these hydroxyaldehydes and hydroxyketones, particularly beta hydroxyaldehydes and beta hydroxyketones, you can get a dehydration in a subsequent step to give you this alpha beta unsaturated compounds. And the driving force for these reactions going forward is that this double bond is conjugated with this double bond. The carbonyl C double bond O is conjugated with the CH, which is present at this position, because double, single, double is like conjugated double bond, and they are resonance stabilized. That's why the dehydration is quite facile, and the dehydration can happen in the presence of acid or can also happen in the presence of a base. So really facile going forward, dehydrating, generating alpha beta unsaturated carbonyl compound, which is resonance stabilized, which is pushing the reaction to the forward direction. So that means these aldehydes and ketones can react to give us alpha beta unsaturated compounds, which have quite interesting chemistry in themselves. And we'll look at that in few minutes. So you might wonder how the dehydration can happen in the base, presence of a base. Normally we see dehydration happens in the presence of acids. So typically if you have an alcohol present in a molecule in the presence of acid, the alcohol gets protonated to give you a OH plus system like that. And then the dehydration is quite facile, then the bond breaks and you get dehydration like so. But this hydroxyaldehyde or hydroxyketones, they can also be removed in the presence of a base, and the base can remove that proton adjacent to the aldehyde, which is still acidic, and that proton is removed, and then you get that pair of electrons moving here, giving you enolate, and then the enolate comes back, the double bond shifts here, and OH minus is lost to give you the alpha beta unsaturated carbonyl compound. So this dehydration or removal of the hydroxyl group can also happen in the presence of acid or base, leading to the formation of this alpha beta unsaturated carbonyl compound. And the key driving force for this reaction is the conjugation. And this reaction can happen with a variety of carbonyl compounds. It's not limited to just simple aldehydes and ketones, which we looked at. We looked at acetaldehyde and we looked at the acetone, and we found that the reaction happened. But if you have a benzene ring on one side and a COCH3 on the other, the reaction can just take place happily on this side over there, while benzene is not touched at all in this reaction. But the ultimate result is you still get a beta hydroxyketone. So this CH3 is converted in the presence of a base into a CH2 minus, and then O minus here, and the benzene ring is still intact. We can call that just a phenyl ring. A pH stands for phenyl ring. And then this CH2 can attack that carbonyl over there to give you the corresponding intermediate hydroxyketone. And then the dehydration of this hydroxyketone give you the alpha beta unsaturated carbonyl or ketone compound in this case. Many times the student asked me, do we need to remember all these chemical structures? As long as you know the functionality that is involved in the chemistry or the chemical reaction, you don't need to remember this reaction as it is. All you need to know is what COCH3 group is doing and concentrate on that. And then the other substituent doesn't change. The other substituents are just present as benzene ring, not participating in the reaction at all. So you don't need to remember that there's benzene here and a benzene there. But in the end, you just concentrate in the middle part, and then the other benzene can simply be added at that particular position. And the same thing applies to this cyclohexanone. So we saw the reaction of acetone just now in the earlier slide. Acetone can also be written as just like that. And now we are looking at the same reaction for cyclohexanone. All you need to do that, imagine that this part of the molecule is not there at all, and you're doing the reaction of acetone just like the cyclohexanone. So what happens here also in the case of cyclohexanone, you can imagine that if I draw the other cyclohexanone upside down and say that what's going to happen in the presence of a base is that you're going to remove one of the protons that is present on the CH2 here to generate that carbon ion. And then this can attack that carbonyl over here, and this can move over here. And end result of that attack is going to be the formation of this particular intermediate. And you can see that this intermediate here is again an hydroxy ketone, and again this is the part of the molecule that is important. The rest is just cyclohexanone part, and the dehydration here is going to lead to the formation of this alpha beta unsaturated carbonyl compound. One thing you might ask is that when we are dehydrating this alcohol, why does it dehydrate to put a double bond over here? Why doesn't it dehydrate the other way? So the question you might ask is that when we are dehydrating that alcohol, why don't we get the carbonyl over here and cyclohexanone over here, and the double bond goes into the ring rather than going over there. So if you remove the proton from this side over here or the other side, it doesn't matter, it's the same product. Hydrogen here, and hydrogen on that side over there as well. So if we dehydrate it this way, the double bond will go there. So the question is, why doesn't this product form and this one forms in very high yield? The reason is that this double bond is not conjugated with a carbonyl. You can see that there's a double, single bond, double bond. So it's not conjugated. Here you got a double bond, single bond, double bond. So this is conjugated with a carbonyl group. That's why it's formed. And that's why the reaction is pushed toward the forward direction, because of this conjugation that is there in these molecules. Okay, so far we looked at this reaction where the aldehyde and the ketone were the same molecule. Aldehyde reacting with itself, ketone reacting with itself, giving us the product. Is it possible to react an aldehyde with a ketone? Because we saw earlier that acetone can react with itself to give us this hydroxyketone, which can then dehydrate. But can we do this reaction where one side is aldehyde and the other side is ketone? If you play around with this reaction quite carefully and select your starting materials carefully, you can get useful synthesis when you react one aldehyde with a ketone or two different types of reactants. So typically, if you take benzaldehyde and react it with acetone, you will get this cross-condensed product where aldehyde reacts with ketone to give us this product in high yield. There's a reason for that. The reason for that is, if you look at this aldehyde here, it doesn't have any hydrogen over here. There's no hydrogen present adjacent to the aldehyde. So we can't really remove that proton, right? And we know that an aldehyde is more reactive than a ketone from our first year chemistry, okay? So that means if there's no hydrogen here, it cannot remove that. We can't really remove that proton. So the aldehyde has to react only one way. And we know that acetone can generate CH2 minus, C double bond O, and a CH3, which we saw in the earlier slides. So the question is, how can we make it react with that aldehyde? So one reason is aldehyde is more reactive than the ketone itself. So this is going to preferentially attack the aldehyde. Second one is that we can use also excess of one reagent. So if we use excess of one reagent over the other, then this will preferentially react with that as well. Okay, so this forms enolate quickly, can react with aldehyde, dehydrate, and give us that conjugated product. And now the conjugation is present between the carbonyl double bond and the benzene ring. So there's a double, single, double, single, double, single, double, single, double, single. So it's like a fully conjugated system, and that is the driving force. So that means you can react two different compounds in this reaction to give you a product, a useful product. Otherwise, you get a big mixture. So the next question which arises is, we're going to try to get a little bit more complicated here, that what if the two carbonyl groups are present in the same molecule? So the example we got here is a 1,4-diketone and a 1,5-diketone compound. By 1, 4, I mean there is 1, 2, 3, and 4. So there's a 1-4 relationship between the carbonyl compound, and this is 1-5 between the two carbonyl compounds. And you can imagine again that one of the CH3 at the end here can form an enolate, form carbanion. That carbanion can attack the other carbonyl group to give us a cyclic hydroxy alcohol or hydroxy ketone. And then hydroxy ketone can dehydrate to give us the conjugated compound here. So you can get a cyclic 5-membered ring system forming in that reaction. There is an alternative reaction possible. If you remove the proton from this CH2 rather than the CH3, you can attack that carbon onto the carbonyl. But in this case, the ring that will be formed will be a 3-membered ring. So 3-membered rings are not very stable. So it's not going to form. Only 5-membered ring will form. And the same applies to 1,5-diketone. You will get a 6-membered ring if you remove the proton from this side and attack onto the carbonyl over here. And you will get a hydroxy ketone. And the hydroxy ketone will then dehydrate to give us this conjugated compound. If you take this carbanion here, then you will have 1, 2, 3, 4, 5-membered ring. 1, 2, 3, 4-membered ring, and 4-membered rings are not stable compared to 5 and 6-membered rings. So that's why you get the 6-membered ring forming in that reaction. Think about it. If you make it 1,6-diketone, what will you get? You need to think about it. I'll leave it to you to think. So the next question then is, can we try to condense 2 ester molecules? So far, we have condensed 2 aldehydes, 2 ketones, aldehyde and a ketone together. And the ketones were present in the same molecule. We tried to condense them together to cyclic compound. Can we condense 2 ester compounds? The answer is yes. And this type of condensation reaction, when you condense 2 ester molecules, is called as a Claisen condensation reaction. Again, I want to emphasize it again that don't get too worried about the complicated natures of the structures. If you think logically, if you think where the reaction is going to happen, you will have no problem in working out what the product of the reactions are going to be. This is your 1 ester shown in blue, the same ester shown in red. If you condense these 2 esters together in the presence of a base, you will get this condensed product, and we call that a beta keto ester. The reason we call that a beta keto ester is this is alpha position, this is beta position, this is a keto group, and this is ester. The blue part you can see is almost intact. What we have lost from the blue part is this OCH3, CH2, CH3 group is gone. And we attached it at this carbon over here, while the rest of the molecule is intact in this red part of the molecule. So that means you can imagine that something is forming. You're going to form some sort of anion here by removing that proton from that CH2. And somehow you're going to react that with a carbonyl, and you're going to get rid of that OCH2, CH3 group. That's the simple logic in this reaction. And if you start worrying, oh, gee, this structure looks very complicated, it's too difficult for me, it's nothing difficult at all, as long as you think logically and see which carbon is going to react with which carbonyl group. And the mechanism is here now, the full mechanism. This is a sodium methoxide rather than sodium ethoxide. It can be sodium ethoxide as well. It doesn't matter. We've been talking about sodium ethoxide being OCH2, CH3 before as a base. Sodium methoxide is equally good. Sodium methoxide is made from sodium and methanol, and this is made from sodium and ethanol. So either of these two is fine. The proton will be removed like before to give you the carbanion. the carbon ion will attack the carbonyl to give you the intermediate O minus compound, because the pair of electron move to the oxygen. This pair will come back and kick out the OCH3 group in this case. So this ester has an OCH3 group. It doesn't matter. And then OCH3 is kicked out. And the end result is a keto ester forming in this reaction. There's your keto functionality, and there is your ester functionality in that molecule. So the two esters condense together to form a keto ester. And this is what we call a Claisen condensation reaction. And the Claisen condensation reaction doesn't have to be between the two molecules of the same ester, just like we saw in the earlier reaction that the aldehyde and the ketones can be different molecules. Similarly here, the two esters can be different molecules. So this is one ester over here. This is the second ester over there. And you can see that there are two different molecules, two different ester compounds. And the end result is again a keto ester formed in that reaction. And again, if you think logically that you remove this proton here from CH2 to generate your carbon minus, and that carbon is going to attack your carbonyl over here, moving that electron pair over here. And then this pair is going to come back and then going to kick your OCH2, CH3 out to form that keto ester compound. So again, from one of the esters, OCH2, CH3 is lost while the second molecule is intact, and you get this crossed aldol condensation product. And again, the idea is that there is no enolizable CH present next to that carbonyl in one of the esters. So that doesn't matter. If you manipulate with your reaction conditions and the product or starting compound, you can get the desired product quite easily. Also, the Claisen can be done between a real ketone and an ester as well. So it doesn't have to be between two different esters or two same esters. It can be a ketone and an ester as well. And again, you can get useful compounds from these kinds of reactions. And the Claisen condensation between a ketone and an ester gives you a diketone compound, because here both the carbonyl groups are a ketone group, and hence this is a diketone compound. Excuse the writing because writing pad is hard to write with. Diketone compound. Okay, so again, mechanistically quite easy to make sense out of that. You generate this, you attack that carbonyl over here, and you move that pair of electrons across. This pair will come back here, and then this group will get kicked out to give you the corresponding diketone compound, where CH3CO comes from this red ester, and the ketone is present as it is. And you might ask, why does it go this way? Why don't we lose a proton from this CH3? The reason is that CH2 adjacent to a ketone is more acidic than a CH3 adjacent to an ester. So that means this will be preferentially removed first and then attack the ester to give us the desired ketone compound. Okay, I think we are nearly coming to the last topic now. This reaction again can be carried out when the two esters are present in the same molecule. So this is an example of two esters being present in the same molecule. And typically this reaction works when the relationship between the two esters is 1,6 or 1,7. What do we mean by 1,6, 1,7? So that's 1, that's 2, that's 3, 4, 5, and 6. So the relationship between the two esters is 1,6 here, but it will also work quite well with the 1,7 diester compound as well. Okay, and logically again, you can imagine that one of the CH2 here will get deprotonated to form that C minus. This will attack the carbonyl, and then that pair comes back and kickstart OCH3 minus to give you this cyclic diketone compound where you got a keto group and an ester group. So just like the other diketone cyclization reaction we saw when the two ketones were present in the same molecule, when you have two esters present in the same molecule, with 1 and 6 relationship, you can get a 5-membered or a 6-membered ring. And this reaction is called as a Dickmann condensation reaction. Okay, so that's quite easily done. Just base and heat it up and you get your product end of the day. Okay, let's just, last bit I want to cover is over the next 5 to 10 minutes, and then we can have questions at the end, is the reactivity of the compounds which are alpha beta unsaturated compounds. Just now we learned that ketones and the aldehydes can react with each other or amongst themselves to form what we call is alpha beta unsaturated carbonyl compound. This is an example of an alpha beta unsaturated carbonyl. And that creates an interesting reactivity within these compounds. So typically we know from first year that the carbonyl carbon is more reactive to nucleophiles because the negative charge is more located towards oxygen and the positive is towards carbon. And if you draw the resonance structure here, put a positive on the carbon and negative on the oxygen, and if there's a pair of electrons, the double bond present adjacent to that carbonyl carbon positive, this pair of electrons can have a resonance structure where you can move that double bond across here. And if you move that double bond across here, the positive charge goes onto the carbon here. So that means this is an electrophilic site. And if you have a nucleophile, the nucleophile can attack this particular carbon over there to give you an addition product. So the alpha beta unsaturated carbonyl compound, your nucleophile can attack directly the carbonyl group if there is no double bond present adjacent to it. This is the direct addition we have learned in first year. Carbonyl compound reacting with nucleophile to give you the alcohol. But if there's a double bond present next to it, then the nucleophile can attack that carbon to give you what we call a conjugate addition product or Michael addition compound. So this name for this reaction is what we call a Michael addition. So typically in carbonyl compounds, the nucleophile reacts with carbonyl to give you alcohol. But when there's a double bond present, which is in conjugation, you can get what we call a conjugate addition reaction rather than the direct addition reaction on the carbonyl. And this conjugate reaction is called as Michael addition reaction. And this reaction is also very much dependent upon the nature of this nucleophile. If nucleophile is very reactive, then will attack the carbonyl compound. But if nucleophile is less reactive, less basic, then it will do the Michael addition reaction. Say, for example, if this nucleophile is an amine or a thiol, it will do a Michael addition reaction or a conjugate addition reaction. If this is a Grignard reagent, which is very, very reactive, it will react directly with the carbonyl compound. We'll see the list of reagents which attack directly versus Michael addition in a minute. So what I mean is that if you have an amine functionality, this amine functionality, instead of reacting with this carbonyl group here, it will react with this position of the carbon by doing a conjugate or Michael addition chemistry to give you that addition compound where you introduce nitrogen into the molecule. So instead of this nitrogen attacking that carbonyl here, it attacks that double bond. It doesn't have to be an ester. It can be an aldehyde. It can be a ketone. It'll be the same reaction. So you can have that as a hydrogen, which is an aldehyde, or you can have it as a ketone, you will still get the same Michael addition or a conjugate addition reaction happening at that position over there when you react that with an amine or a thiol. So just to give you a list where Michael addition reaction is going to happen and where direct addition going to happen, it depends upon the nature of the nucleophile you have. And this is the Michael or conjugate addition chemistry, where the nucleophiles are cyanide, sulfide, organocupride, amines, halides, and also I told you that this can be thiols, and thiols are represented by sulfides. Sulfur nucleophile will attack onto that carbon over there in a Michael addition manner to give you the Michael addition product or conjugate addition product. Typically, they are weak nucleophiles. But if there is a Grignard reagent, there's lithium aluminum hydride, organolithiums, they still will react directly with the carbonyl compounds. So lithium aluminum hydride, you have a hydride reagent, which is a very strong nucleophiles. Grignard reagent has typically an R minus, which is again a very strong nucleophile. It will react in a direct manner compared to the weaker bases. Okay, the last two slides. Another reaction which is possible in the case of the conjugate addition or the Michael addition is what we call an Robinson annulation. Annulation is a term that is used when you fuse a ring onto another ring which is already present in your starting material. So if you look at this starting material, here is cyclohexanone. If we fuse another ring to that, this is what we call an annulation. And the result of annulation is that you get fused rings. You get two rings fused that is formed, and just like an addition of any ring. And the Michael addition reaction we talked about can also be carried out by an enolate. So if you take the cyclohexanone, remove a proton from cyclohexanone, this C minus that is generated can also do a Michael addition reaction onto the CH2 or a conjugate addition reaction onto the CH2 to form this CH2, CH2, COCH3. So basically the carbon ion has added onto the alpha beta unsaturated carbonyl compound. And now if you look at this compound carefully, you can see that this CH3 can be removed as well by a base. The proton can be removed by a base from here, and that can then attack that carbonyl which is sitting next to it, moving that pair of electrons over there to give you the hydroxy ketone compound, which we have seen before, the corresponding hydroxy ketone when the aldehyde or the ketones react together. So that's a ketone reacting together to form this hydroxy ketone compound. And that reaction is called as an aldyl condensation reaction. And the dehydration happens to generate this double bond that is in conjugation with a carbonyl compound. So that's the driving force for this annulation reaction to form that conjugated carbonyl compound. So there are two components to Robinson annulation. First component is that you get a Michael addition adjacent to the carbonyl, and once Michael addition has happened, then you get an aldyl condensation between the two carbonyl compounds we have to give a ring hydroxy ketone, and that hydroxy ketone is then dehydrated to give you alpha beta unsaturated carbonyl compound. And this is my last slide of the day, giving you the actual mechanism of the Michael addition reaction, the aldyl condensation reaction, to give the fused compound, which I had it on the last slide. And the mechanism is self-explanatory. And I gave you some hints already in the last slide what the mechanism was. You generate that carbon ion in the presence of a base. You do a Michael addition or a conjugate addition chemistry to form that CH2, CH2, CO, CH3 shown on the last slide. So that compound here, this compound here is exactly the same compound which is shown over here in this slide. That compound over there is just drawn now in full detail mechanistically. And then you remove that proton from the CH3, and that CH2 comes and attack that carbonyl. That pair of electron moves up there to give you the alcohol, and then you get a dehydration to give you a conjugated double bond with a carbonyl, and that's the driving force for this reaction. And this is what we call a Robinson annulation. And Robinson annulation is used to fuse rings together. And you can continue with this chemistry if you like, and fuse another ring over here on that side, and so on, and build up these fused ring systems as shown here. All right, I think I covered enough already. I stop here for now, and I'm happy to answer any questions which people might have.
Thank you, Professor Naresh Kumar. It's really I do really enjoy the lecture. It was very clear and concise, and I'm quite sure that all the audience couldn't agree more. I think you put a lot of work into the slide, and this is the time for having questions. And I was wondering if the audience have any question. Please, you can raise the hand, or you also can text in the chat box. Any questions? Maybe Prof. Asep has a question. Prof, still mute.
Thank you, Bu Siti Aisyah. On the slide number 65.
65.
65. Okay. Yeah, you explain the competitive reaction between hydrogen at C alpha cyclohexanon and methyl group from the methyl phenyl ketone. Yeah. Okay. Could you explain more why the first what I mean?
Okay. So the question here is that why do we remove the proton from this CH3 to form CH2 minus and react with the carbonyl? There are a few other places where the proton can be removed. For example, you have a CH2 on this side as well.
Yes.
And you could say, why don't we remove this proton rather than the proton over here? So if I remove this proton here, I just draw the structure again at the top. Your cyclohexanone, sorry, excuse me, that, oops, the writing is a little bit hard with the keypad. So if you draw the carbonyl over here and we remove this proton instead, so what's going to happen is we have a minus over here. And then we have our CO CH3 over here. But if we attack that onto that carbon over here, we can see that the ring size I'm going to get is 1, 2, 3, 4-member ring. And 6-membered rings are thermodynamically much more stable than 4-member ring. So that's why the reaction doesn't take place from that removal of that proton. You are right that you will get more stable enolate that way because it'll be more substituted. But since it's giving a 4-member ring, it's not favored very much. But there is another possibility as well. You could say that, why don't we remove this proton over here, because there's a proton here as well. And then that can attack the carbonyl group on the other side. So what I mean is, if I just draw that down, so there are a few possibilities in this molecule where the proton can be removed. So we say, why don't we remove the proton So if we have CH2, CH2, CO, CH3, and we remove the proton over here at this position because that's also adjacent to the carbonyl, and attack that onto that carbonyl over here. And then you can see we get again 1, 2, 3, 4-membered ring. So that doesn't help either. But there's another possibility. We could go from this side rather than on that side, and then attack that carbonyl. But then you're going to get funny fused ring systems. And that's why I think you're right that there are a few different products possible from that starting intermediate, but only one of them predominates because it's forming 2 6-membered rings, which are thermodynamically more stable. A 6-membered ring is much more favorable than a 4-membered ring. And also the conjugation, which you get after you dehydrate that molecule, that it all goes towards that sort of product. So there may be intermediate products formed in the reaction in small amount, but as the equilibrium moves towards the more stable product, all these intermediates then start to follow in that direction rather than giving a mixture of products. You get predominantly one product forming in these reactions.
Okay, thank you, Prof.
No problem.
Okay, any other questions from students? I think this is quite a great chance to ask Professor Naresh.
Don't be shy, just ask
Yes.
anything.
You also can ask the question in Bahasa and then I or Bu Vidya will translate it for you.
Someone is raising hand, guys.
Oh yes, of course, yes. Please, San Paris.
Okay, thank you, Prof. Naresh. I want to ask you about the aldol condensation that one of our students asked. So,
Yep.
may you can share screen your slide about aldol condensation?
Yep.
About the last example, maybe.
Okay. Last example. Sure. Yep. Okay.
Okay.
Yeah.
I want to ask, except the unstable ring that maybe this structure will produce,
Yep.
does the pH influence the majority or minority of the product, maybe? The pH of the...
pH, yeah. So it's okay. So the question is, can the pH affect the formation of the product?
Yes.
So as you can see here, I got base all over the place. And you may recall that in the earlier example, when we looked at the aldol condensation reaction, we learned that the dehydration can be carried out in acid or base. So it doesn't matter. So I think I had it on this slide that the dehydration can be carried out in the presence or acid or base. So that's here. So the dehydration can either be base or acid catalyzed. So since we are using base in that reaction, we didn't use any acid at all. So that means that dehydration in that reaction happens in this manner here, where you lose the OH as OH minus, which then protonates to give you water. So the aldol condensation reaction can be carried out in acid or base. The dehydration can be carried out in acid or base. It doesn't matter, because the end product has this conjugated double bond with the carbonyl group, and that is what is driving the reaction forward. So typically in aldol condensation reactions, you can basically add water at the end of the reaction and you will get your product. But in some cases, you might have to make the solution acidic to be able to isolate your product at the end. So it's just a matter of depending upon your starting compound you're using. If you add water and the product crashes out, it's good. But if the product doesn't crash out at the end, you normally add acid at the end of the reaction. And the purpose of the acid is that, it just basically helps with the dehydration as well at the end of the day, and neutralizes all the base that is present in your product. So pH can be important, but not so important for this reaction, because the aldol condensation here can be carried out in the presence of a base. So that means you can get your product just by heating it in base and water at the end.
So the possibility which pH, CH that maybe can be a base in this reaction is the same.
Yeah, the result is the same. Yeah. So the aldol condensation reaction can also be carried out in acid as well. Remember in the last week's lecture, I told you that enols can form in the presence of an acid or a base, like when you have a ketone and a CH2 next to it, you can generate the enolate or enol in the presence of acid, or you can generate it in the presence of a base. So the aldol condensation reaction can be carried out either in the presence of acid or in the presence of a base.
Okay, Prof, thank you.
Okay.
Okay. So Paris, I was wondering, because you asked about the pH, did you mean the pH of the reaction, or do you mean the pH of the, because we have a lot of H alpha that also can,
Yes.
the pH of the experiment, or the pH of the H of the C, because I think that every C has the different pH. I was wondering which one is the question.
I think that's a very good point, because
Thank you.
the ketone compounds are acidic themselves.
Yeah.
So there is a pKa associated with them, and they are acidic. And also the solution can be acidic or basic. So I think the question was more on toward the solution, as I understood it, that the reaction is carried out under basic conditions, and is the pH important there?
Okay.
But I think that's a very valid point.
Okay. Yes. Thank you. Okay. Because I saw one raise hand and then turn it off. So any questions? Okay. If there is no question anymore, I think this is it's almost 6 here. And then I think this is the end of this session. Thank you, Professor Naresh Kumar, for really informative lecture. And then I think maybe some students need to digest, because it's quite some reaction. But basically, this is talking about the H attached to the carbon alpha, and we are talking about the nucleophile, and then also the result can be different because of different type of the reagent. Yeah. So I think if you try to do step by step, I think this is really quite nice and easy to understand, Prof. Yeah. So I think thank you very much, Prof. Naresh. Also, thank you very much for all the students attend this lecture. Also, thank you for all the lecturer from chemistry department. And then maybe see you all after in the 2 weeks after this one. Not next week, yeah, Bu Vidya. Next week there is no lecture from. Okay.
Yes.
Yeah.
Yeah, it will be on 6th December.
6th December.
Or no,
November.
last of November, I think.
Yes. 14 days.
Yes.
Yes.
I have it in my diary. I have it in my diary. So
Okay. Okay. Thank you, Prof. So see you in 2 weeks.
Yeah.
And then thank you very much for all the lecture. Also, thank you all students for attending this lecture. Thank you.
No problem. Thank you for attending. I will see you soon.
Okay.
Thank you, Prof. Naresh.
See you. Okay. Bye.
Prof. Naresh. Yeah. See you next.
Yep. Bye.
Oke, ya mahasiswa, Ibu dan Bapak, terima kasih sudah hadir di acara lecture ini, dan kita akan ketemu kembali berarti 2 minggu setelah hari ini, ya. Jadi tanggal 20 sekian, 23 November mungkin. Ya, terima kasih Prof. Asef, Bu Amel, Bu Vidya, Bu Fitri, saya masih lihat masih ada. kemudian ibu bapak yang lain yang saya tidak bisa sebut juga mahasiswa. Kita tutup dengan membaca hamdalah. Alhamdulillahirrabbilalamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih Bu Ais.
Terima kasih semuanya.
Terima kasih Bu Ais, hatur nuhun.
Hatur nuhun, Bu.